Picking up where we left off, we just discovered the power rule. It's going to be huge for the rest of our course. For now, we're thinking of, is there some shortcuts? Are there some formulas that we can get derivatives of polynomials really quick? And it turns out we'll be able to do polynomials, the derivatives, in just one step, which is incredible. Let's sit on this for a little while. Let's let it soak in. I'm going to run us through a bunch of quick examples. Starting with, let's look at f of x equals x raised to the 56. I would not want to try this one out with the definition of the derivative raising to the 56 power. So the formula comes in handy. What is the derivative there? F prime of x, if we follow that form, would be, well, the 56 would move down in front, and we'd drop the power by 1. 56x to the 55. Done. We got it. No other steps in between. That's it. Now that we know the power rule. Let's try another one. How about y equals x to the negative 2, a negative exponent? Well, same formula. That negative 2 is going to move down. Then we're going to subtract 1. I'm going to call it y prime. Y prime equals negative 2, x raised to the, subtracting 1, negative 3. Negative 2, x to the negative 3. One step, done. Okay. How about this? And we're going to try out this notation now. D over dx. Oh, it looks like you see the answer already. Oh, I should have done this. D over dx, x raised to the 5 over 2. Hey, a fractional exponent, no problem. Same power rule. The 5 over 2 moves down in front, and then we subtract 1. So if the 5 over 2 moves down, that's 5 over 2. X raised to the, and subtracting 1, subtracting 2 over 2 gives you x raised to the 3 over 2. There's the derivative. That'd be a fun one with the definition. No. Okay, let's try another one. Oh, this is interesting. H of x equals x raised to the natural log of 3. Well, the natural log of 3 is a number like any other number, so we can still just move it down and subtract 1. Here's h prime of x, the natural log of 3, times x raised to the natural log of 3 minus 1. Well, I guess that would have to be it. Okay, I've got one more. Ooh, this is interesting. How about y equals the cube root of x? Okay, to do this one with the cube root, really any root, we need to think of it as a power, right? We've got the power rule deals with x raised to a power. So think of this as x raised to the 1/3. And then you can apply the power rule. The 1/3 will move down. We'll subtract 1. I'm going to call it dy over dx for the derivative. The 1/3 moves down in front, x. And if you subtract 1, you're subtracting 3 over 3, x raised to the negative 2/3. There it is. Now, if you prefer to not answer this with a negative exponent, you could also tuck that down into this denominator, 1 over 3 x to the positive 2/3. Either way is fine. Actually, we kind of lean towards the negative exponents. Would we do derivatives just because we're going to see them so often? But that works well either way. Okay, very cool, very cool. Where are we going next? Okay, so we know how to do x raised to any power. But sometimes in polynomials, we see constants, right? So let's look at what is the derivative of f of x equals c, where c is a number or a constant. Well, let's go back to the definition of the derivative. Okay. We'll need, I'll show you all this. For a constant, f of x plus h equals the same constant. Right? There's no x to plug in or to replace, so it's still equal to c. So then if you were to go ahead and do the definition, the limit as h approaches 0, c minus c over h, well, clearly that's the limit as h approaches 0 of 0, and we know the limit of any constant is just that constant. So the derivative of a constant, f prime of x, would equal 0. Always, for any constant, the derivative is always 0. And I've got a graph depicting that and explaining that, if you want to see it visually. So, right, if our function is c, y equals c, that's a horizontal line, right? Well, no matter where you pick x, what is the tangent line doing? Here, if all you have is a line, then the tangent line is actually that very same line. And what's the slope of any tangent line anywhere you pick? Well, it's always going to be 0, no matter what you pick x to be. And no matter what the constant is, slope is always 0. Oh, that's interesting. Okay. Moving on. Oh, okay. Well, let's say it formally. The constant rule, before we move on, the derivative of any constant equals 0. Okay, kind of noted that officially now. The constant multiple rule. So this will also involve a constant, but in a different way. If it's just a constant, then it's 0. But what if you've got a constant being multiplied by a function? So we're going to say d over dx, the derivative of c times f of x. In this case, what you need to do is we just that c just sort of carries along, and we take the derivative of f prime, or of f of x to get f prime. So the derivative of c f of x is c f prime of x. Actually, that same the same format of the rule would apply to limits as well. If we had a number times a function, then the limit would be the function times the limit of that, the constant times the limit of that function, I should say. The constant multiple rule. Okay, let's see it at work. We've got a quick example here. So what if we wanted the derivative of 7x to the third? We're going to say, okay, 7 is like a constant multiple, so that's just going to carry along, and I'm going to multiply it by the derivative of x to the third. Well, the derivative of x to the third, we know, is 3x squared. So that's going to multiply, and my final answer is going to be 21x squared. There you go. I've really shown you all the nitty-gritty details here. Truth is, in practice, just think of it as the 3 multiplies down. 3 times 7 is 21. And the power drops by 1. So you won't actually show these middle steps. You'll just go straight to the end when we are doing problems in this section. But it's nice to see it broken down when you first learn it. Okay, that's the constant multiple rule. There's one more piece we need before we can say we're officially ready to do a polynomial. What if you're adding or subtracting two functions? So we're going to call this the sum/difference rule. So we're saying the derivative of f of x either plus or minus g of x. I'm adding or subtracting two things. Well, it works out pretty nice. I can simply do f prime of x, either plus or minus whatever the original was, g prime of x. So I take the derivative of f, I take the derivative of g, whatever those are, and then I just either add or subtract the results, whatever I need. The same would be true of limits, right? If you took the limit of a sum, then that's the sum of the limits, and it sounds really impressive when you word it that way, like here with the derivative. The derivative of a sum is the sum of the derivatives. Anybody asks you what you learn in today's video, tell them the derivative of a sum is the sum of the derivatives, and it will sound really impressive. Okay, we're going to put all these together and look at this example right here. F of x equals 2x to the 9th plus 4x to the 7th minus 3x to the 3rd plus x squared minus 6. We got a full-blown polynomial. We're going to take the derivative in one step. Are you ready? All we got to do, the sum difference rule says we can just look at them one at a time. So we'll take this derivative plus this derivative minus this derivative plus this minus this, and we'll have it. It'd probably be better if we were to write them out one at a time, and that's what we would do if we were in class, but I'm just going to show it to you. So f prime of x, what here? So the 9 multiplies down, 18 x to the 8th. Okay, then moving to the next one, plus the 7 multiplies plus 28 x to the 6th minus the 3 multiplies 9x squared plus 2x. Well, that derivative, x squared, the derivative of that is 2x. And then why don't we have anything here? Well, because the derivative of 6, we'd be saying minus 0, but we're just not going to write anything there. So there is your derivative, 18x to the 8th plus 28x to the 6th minus 9x squared plus 2x. Imagine doing that with the definition of the derivative. No, thank you. We can do it in one step with these handy rules. Okay, awesome. We've got a problem now. You could think of it as sort of an application of the things we've just learned about derivatives. We can really increase the level of difficulty with the questions we now ask because of how fast it is to take derivatives now. We don't just have to say, hey, just find the derivative, but now because derivatives are very quick, we can really make things more challenging. Find all points x comma y on this function, y equals 4/3 x to the 3rd minus 4x squared minus 12x plus 1. All the points xy on that function where the tangent line is parallel to y equals negative 12x plus 5. Okay. Interesting. How are we even going to start this? Well, we're talking about tangent lines, so obviously that involves derivatives. We say the tangent line is parallel. Hey, what's true about parallel lines? You guys remember? Parallel lines, they have the same slope, right? All parallel lines always have the same slope. So we want to know where the tangent lines of this are parallel to this other line. Well, so that means any tangent lines need to have the same slope as this line. Well, what is the slope of this line? And of course, it's the 12, all right? Okay, so what we got to do, once we recognize we're looking for tangent lines with a slope of negative 12, we need to take a derivative. Let's do that. And we'll tie it all together. So this derivative, let's just call it y prime. Here, if you multiply this 3 down, it will cancel, and you'll simply get 4x squared minus 8x minus 12. Hey, the derivative of minus 12x, the derivative of the x is 1, right? So think of this as the derivative is negative 12 times 1, so negative 12. And then the derivative of this plus 1 is 0. Okay, so we got y prime. So we want to know, let's see here, if that's the derivative is, this describes the slopes of the tangent lines, right? So we want to know, when are the slopes of the tangent lines equal to negative 12? What x values will cause or make y prime equal negative 12? Always remember the derivative means the slopes of the tangent lines. So when do these slopes equal that slope? Well, this won't be too difficult, at least to set up. What x values cause this to happen? Well, we're just going to put a negative 12 there and solve. Negative 12 equals 4x squared minus 8x minus 12. And this one turns out to be fairly simple, right? We can add 12 to both sides. Set it equal to 0. Do some factoring. Factor out of 4x times x minus 2. And I think I can go ahead and pull this thing up. Solve that. We've got x equals 0 and x equals 2. So we found the x values that make y prime equal negative 12. We're not quite done. The original problem said find all points x comma y. So we need to find the y values of each of these x values. Let me just show you all that here. So at x equals 0, we're going to put that back, plug 0 back into the original y, which is now off the screen. But when we do that, y of 0 is going to equal 1. We'll do the same thing with 2. Y of 2 equals negative 85 over 3, turns out. Keep the exact value there. Don't round that. So the points are 0, 1, and 2, negative 85 over 3. Okay, so after we finish, we got one more part, but I'll also make a Desmos video on this, and we'll take a look at this problem for sure. See you in this is part 3, isn't it? Part 4? Wow.